So this actually, you might recognize, is the Hubble Space Telescope, who has brought us so much joy. And it's quite a story. The Hubble Space Telescope, I want to say, was one of the first to go up and do what it does, bring the beautiful images that it does. It actually has an assortment of cameras, but it takes pictures in the visible region of the electromagnetic spectrum. But I have a few slides to kind of talk about why would you want to put a telescope in outer space orbiting the Earth. And the answers might be obvious. One is that you are above the lights that make viewing so difficult. We, since the invention of electricity, have been getting more and more light at night. The other thing is that the Earth's atmosphere can kind of definitely add some effect, what we call twinkling, and you get beyond that and things are better. And the other thing is the Earth's atmosphere, fortunate for us on the Earth, is good at blocking out some forms of energies that we really want to take a look at. So kind of those regions in general. So this is actually a figure I don't know if you can kind of see a map of the world when that part of the world is in darkness, and at nighttime, I guess I should say, and you can kind of see the lights come on. And so there is a lot of light pollution out there. A shout out to International Dark Skies Association. They have made it their mission to go about working on excess light pollution, because it's hard to use telescopes to see, to enjoy the nighttime sky, and there's all sorts of other reasons, including life it's not supposed to have all the light that we've got at night. And this is kind of a close-up of North America. So which city do you live in, right? Lots of lights. So the second one was, if you put a telescope in orbit, then you don't have what we call twinkling. If you heard twinkle, twinkle, little star. Okay, so if you've heard planets don't twinkle and stars do, actually, there's something to that. Planets basically kind of have a disk component to them that the twinkling doesn't work with them as much. Lights, stars that are kind of more like points of light, actually, as in the Earth's atmosphere, we have different temperatures of air, especially, or moisture of air. It basically kind of refracts, bends the light. So down here on Earth, we kind of see the star dancing. That's twinkling. So anyway, left to right, you see the left one is from the same field of view as the right one, but the right one is from the Hubble, and the left one is from a land-based telescope. So the last one is to try to, if we want to see energies in wavelengths that the Earth's atmosphere blocks out, we have to get above the Earth's atmosphere. So this is kind of a slick little figure. The way this works is you see the different energies: gamma rays, X-rays, ultraviolet, visible, infrared, and radio. And then you can see the if the arrow doesn't get down to the Earth, that means it's blocked out. Okay, so we have the Earth down here. So that's kind of cool. So actually, you see here in the visible region of electromagnetic spectrum, light is allowed to come through, but all other forms of light are partially blocked. Well, I shouldn't say. We have radio waves over here that are also allowed to come down. So over here across the top are an assortment of spacecraft: the Fermi, Swift, Chandra, Hubble, Spitzer, and WMAP, okay, that are looking at those different energies as they orbit the Earth. Is that not cool? What? This is a kind of a close-up of Chandra. Chandra's looking at the X-ray signals that are coming from distant objects. Close-up of Chandra. So another trick there's two more tricks I want to show you with regard to telescopes that are land-based, telescopes on the Earth. One of them is called adaptive optics. And so what adaptive optics do, as I understand it, is they send up a signal via laser, and basically they look for kind of wiggles in that signal. Okay, they observe how that signal behaves in the Earth's atmosphere, and then on the spot they basically adjust their mirrors according to try to cancel out turbulence in the Earth's atmosphere. Is that not cool or what? So kind of left to right, they're looking at the same object. The left one, we see poor resolution, okay? It looks like one object, but the right one, you can actually see the two objects. Okay. Adaptive optics, left, right. Left without adaptive optics, and right is with adaptive optics. Okay, this is pretty cool. Jupiter has 4 moons that Galileo saw, and actually Io is one of those 4 moons around Jupiter. We call it one of the Galilean moons. But Io is a pretty cool little moon in and of itself. And so the right one is with adaptive optics looking at the moon of Io. That's pretty cool. So the last trick I want to show you is actually something looks like a gang of satellites, doesn't it? Okay, but actually these are a gang of dishes that are telescopes, or they're a gang of radio telescopes. And the thing about radio waves is they are so long. Remember we saw a little bit ago a radio telescope that was humongous. Well, this is kind of a way around that. Basically, you have an assortment, an army of telescopes all looking at the same object, and they recombine their signal to try to kind of, or not try, but to accomplish gathering information about those long wavelengths. So this one actually is in New Mexico, called a Very Large Array. Interferometry is what we call this. And the last one, just to kind of get you thinking, is wouldn't this be interesting if this is what the surface of the moon looked like someday, where we took advantage of the moon has gravity. Okay, those things aren't going to float off, right? And with regard to an atmosphere, there's basically no atmosphere. The moon has what they call an exosphere. Yeah, I think we should do that.